Technical protection, source code management, version control systems. Importance and benefits. Version control systems, VCS like Git, allow for tracking changes, collaboration, and maintaining a history of the software development process. Popular systems. Discuss widely used VCS options such as Git, Subversion, SVN, and Mercurial. Access controls. Implementing secure access. Use role-based access controls and two-factor authentication to restrict access to sensitive code. Best practices and tools. Employ tools like GitLab, GitHub, and Bitbucket for managing access and permissions. Case studies. Effective source code management in practice. Google's source code management overview. Google, one of the largest technology companies globally, manages a massive and complex code base. The company's approach to source code management, SCM, is designed to handle the scale and complexity of its operations while maintaining security, efficiency, key practices. Monorepo strategy, single repository. Google employs a monolithic repository, monorepo, strategy, where nearly all of its code resides in a single repository. This approach contrasts with using multiple repositories for different projects. Advantages. The monorepo strategy facilitates code sharing, refactoring, and consistency across the company's projects. It also simplifies dependency management and code integration. Piper and CITC, client in the cloud. Piper. Google uses Piper as its main version control system, which supports the monorepo strategy. Piper is built on top of Perforce, a commercial version control system. CITC, client in the cloud. CITC is a virtual file system that allows developers to work on code directly from the cloud. This setup ensures that developers are always working with the latest version of the code and reduces the risk of conflicts. Blaze build system. Blaze, Google developed its own build system, Blaze, open-sourced as Bazel, to manage the compilation and build processes. Blaze is designed to handle large codebases efficiently and supports incremental builds to save time. Caching and parallelism. Blaze uses extensive caching and parallel execution to speed up the build process, making it highly efficient for Google's needs. Code review and testing. Code reviews. Google mandates rigorous code reviews for all changes. This practice ensures code quality, security, and consistency. Tools like Critique, Google's internal code review tool, facilitate the review process. Automated testing. Google integrates extensive automated testing into its development workflow. Tests are run on every code change to catch bugs early and ensure that new changes do not introduce regressions. Security practices. Access controls. Google implements strict access controls to its code base. Developers have access only to the parts of the code they need for their work, reducing the risk of unauthorized access or accidental changes. Static and dynamic analysis. Google uses static and dynamic analysis tools to detect potential security vulnerabilities in the code. These tools help identify issues like buffer overflows, memory leaks, and other common security problems. Continuous integration and deployment, CI/CD. Continuous integration. Google's CI system automatically builds and tests code changes as they are committed. This practice ensures that the codebase remains stable and that changes are integrated smoothly. Continuous deployment. Google employs continuous deployment practices to roll out new features and updates. This approach allows for rapid iteration and quick delivery of new functionality to users. Key takeaways. Scalability. Google's SCM practices are designed to handle a massive and complex codebase efficiently, demonstrating the importance of scalable solutions in large organizations. Collaboration. The monorepo strategy and rigorous code review processes promote collaboration and consistency across the company. Security. Implementing strict access controls and using advanced analysis tools helps maintain the security of the codebase. Microsoft's source code management overview. Microsoft, a technology giant with a diverse range of products and services, also manages a vast and complex codebase. The company's SCM practices focus on security, collaboration, and efficiency, leveraging modern tools and methodologies. Key practices. Distributed version control systems, DVCS, Git adoption. Microsoft has widely adopted Git, a distributed version control system, for managing its codebases. Git's distributed nature allows for greater flexibility and collaboration among developers. Azure DevOps and GitHub. Microsoft integrates Git with its Azure DevOps services and GitHub, acquired by Microsoft, providing a robust platform for source code management, continuous integration, and deployment. One Engineering System, 1ES, Unified Development Platform. The 1ES initiative aims to standardize tools, processes, and infrastructure across Microsoft's engineering teams. This initiative helps reduce fragmentation and improves collaboration and productivity. Common tools and practices. By using common tools and practices, Microsoft ensures consistency in its development processes, making it easier for teams to work together and share code. Code review and quality assurance. Pull requests. Microsoft uses pull requests, PRs, for code reviews. PRs allow developers to propose changes, which are then reviewed by peers before being merged into the main codebase. Automated testing. Automated testing is a critical part of Microsoft's development workflow. Tests are run on every PR to ensure that changes do not introduce bugs or regressions. Security and compliance. Secure Development Lifecycle, SDL. Microsoft's SDL framework integrates security practices into every phase of the software development process. This framework includes threat modeling, secure coding practices, and regular security reviews. Code scanning and analysis. Microsoft employs tools like CodeQL and static analysis to detect security vulnerabilities and coding errors. These tools help maintain a high level of code quality and security. Continuous integration and continuous deployment, CI/CD. Azure pipelines. Microsoft uses Azure pipelines for CI/CD, allowing for automated builds, tests, and deployments. This setup ensures that changes are integrated and deployed quickly and reliably. Feature flags. Feature flags allow Microsoft to deploy new features to a subset of users before a full rollout. This practice helps mitigate risks and ensures that new features are thoroughly tested in production environments. DevOps culture, collaboration and communication. Microsoft fosters a DevOps culture that emphasizes collaboration between development and operations teams. This culture helps streamline the development process and improves the efficiency of deployments. Continuous improvement. Microsoft's DevOps practices focus on continuous improvement, using feedback loops to refine processes and tools continually. Key takeaways. Modern tools and practices. Microsoft's adoption of Git, Azure DevOps, and GitHub demonstrates the importance of using modern tools and practices to manage large code bases. Standardization. The 1ES initiative shows the benefits of standardizing tools and processes across an organization to improve collaboration and productivity. Security focus. Integrating security into the development lifecycle ensures that code remains secure and compliant with industry standards. Comparative analysis. Similarities. Focus on security. Both Google and Microsoft place a strong emphasis on security, using access controls, code analysis tools, and secure development practices to protect their code bases. Automated testing. Automated testing is integral to both companies' workflows, ensuring that changes are thoroughly tested and validated before being merged. CI/CD practices. Continuous integration and deployment practices are employed by both companies to streamline the development process and ensure rapid delivery of updates. Differences. Repository strategy. Google uses a monorepo strategy, while Microsoft has adopted a more distributed approach with Git and multiple repositories. Each strategy has its own advantages and challenges. Development platforms. Microsoft leverages its own Azure DevOps and GitHub platforms, while Google uses internally developed tools like Piper and Blaze. Conclusion. The source code management practices of Google and Microsoft illustrate the importance of scalable, secure, and efficient SCM strategies in large organizations. By adopting modern tools, standardizing processes, and integrating security and quality assurance into their workflows, these companies effectively manage their vast and complex code bases. These practices not only enhance collaboration and productivity, but also ensure the delivery of high-quality, secure software products. Encryption. Encryption techniques. Types of encryption. Symmetric encryption uses a single key for encryption and decryption. Asymmetric encryption uses a pair of keys, public and private, for encryption and decryption. Applications and software protection. Protect data transmission, storage, and software code integrity. Implementing encryption. Tools and best practices. Use encryption libraries and frameworks such as OpenSSL and follow best practices for key management and secure algorithms. Protecting data in transit and at rest. Encrypt sensitive data both during transmission, e.g. TLS, SSL, and when stored. Code obfuscation methods and tools. Use tools like ProGuard for Java or .fuscator for .NET to obfuscate code, making it difficult to reverse engineer. Balancing performance and security. Ensure that obfuscation does not significantly impact the performance of the software. Case studies. Real-world applications of encryption in software. WhatsApp, end-to-end encryption for secure messaging. Overview. WhatsApp, a widely used messaging application owned by Meta Platforms Inc., formerly Facebook, employs end-to-end encryption, E2EE, to ensure the security and privacy of user communications. This case study explores how WhatsApp implements encryption to protect messages and the broader implications for secure messaging applications. Key practices. End-to-end encryption, E2EE. Definition. E2EE ensures that messages are encrypted on the sender's device and only decrypted on the recipient's device. This means that even the service provider, WhatsApp, cannot read the messages while they are in transit. Implementation. WhatsApp uses the Signal protocol, developed by Open Whisper Systems, to provide robust E2EE. This protocol is known for its strong security guarantees and is widely regarded as a leading standard in secure messaging. Encryption algorithms. Double ratchet algorithm. The Signal protocol employs the double ratchet algorithm, which combines the Diffie-Hellman key exchange, public key cryptography, and a ratchet-based key update mechanism. This ensures forward secrecy and post-compromise security. Curve 25519 and AES 256. WhatsApp uses Curve 2519 for key exchange, AES 256 for encryption, and HMAC SHA 256 for message authentication. These algorithms are considered highly secure and efficient for cryptographic operations. Key management. Session keys. Each conversation between users generates a unique session key that is used to encrypt messages. Session keys are periodically refreshed to enhance security. Pre-keys. WhatsApp uses pre-keys, which are public keys published by users and stored on the WhatsApp server. When initiating a conversation, the sender retrieves the recipient's pre-keys to establish a secure session. Message encryption and decryption. Encryption process. When a user sends a message, it is encrypted using the session key and transmitted to the recipient in an encrypted form. Metadata such as timestamps and sender information are also encrypted to prevent metadata leakage. Decryption process. Upon receiving the encrypted message, the recipient's device uses the session key to decrypt it. This process ensures that only the intended recipient can read the message. Additional security features. Authentication. Users can verify each other's identities by comparing a security code displayed on their devices. This mitigates the risk of man-in-the-middle attacks. Device verification. WhatsApp notifies users when a contact's encryption keys change, which can happen if the contact reinstalls the app or switches devices. Users can verify the new keys to ensure continued security. Key takeaways. Privacy and security. WhatsApp's implementation of E2EE ensures that user messages are private and secure, protecting against eavesdropping by third parties, including the service provider. Trust and adoption. The use of strong encryption protocols and transparent security practices has helped WhatsApp build trust with its users, contributing to its widespread adoption. Regulatory challenges. While E2EE provides robust security, it also poses challenges for law enforcement and regulatory authorities who may seek access to communications for legitimate purposes. WhatsApp's encryption policies have sparked debates on balancing privacy and security. Apple iMessage, securing text messages. Overview. Apple's iMessage is another prominent example of a messaging platform that uses encryption to protect user communications. This case study examines how iMessage implements encryption to ensure message security across Apple devices. Key practices. End-to-end encryption. Encryption by default. iMessage uses E2EE to secure messages sent between Apple devices. This means that messages are encrypted on the sender's device and decrypted only on the recipient's device. Key generation. When a user sets up iMessage, a unique pair of public and private keys is generated for each device. The public keys are registered with Apple's servers, while the private keys remain securely stored on the device. Encryption algorithms. AES 128. iMessage uses AES 128 encounter mode for message encryption, which is a secure and efficient algorithm suitable for encrypting large amounts of data. RSA and ECDSA. RSA encryption is used for key exchange, while ECDSA, elliptic curve digital signature algorithm, ensures the authenticity and integrity of messages. Key management. Public key directory. Apple maintains a directory of public keys for each iMessage user. When a user sends a message, the recipient's public key is retrieved from this directory to encrypt the message. Key derivation. iMessage employs a key derivation process to generate ephemeral encryption keys for each message, enhancing security and preventing key reuse. Message encryption and decryption. Encryption process. Messages are encrypted on the sender's device using the recipient's public key and the derived ephemeral key. The encrypted message is then transmitted through Apple's servers. Decryption process. Upon receiving the encrypted message, the recipient's device uses its private key to decrypt the ephemeral key and subsequently decrypt the message content. Additional security features. Forward secrecy. iMessage supports forward secrecy, ensuring that if a key is compromised, past communications remain secure. Integrity verification. Digital signatures are used to verify the integrity and authenticity of messages, ensuring that they have not been tampered with during transmission. Key takeaways. User experience. Apple's implementation of E2EE and iMessage is seamless and integrated into the user experience, providing strong security without requiring user intervention. Cross-device security. iMessage's encryption model ensures that messages remain secure across multiple Apple devices associated with the same user account. Transparency and trust. Apple's commitment to privacy and security, coupled with its clear communication about encryption practices, has helped build user trust in iMessage. Signal, leading the way in secure messaging. Overview. Signal is a messaging app known for its focus on privacy and security. Developed by the nonprofit Signal Foundation, the app uses advanced encryption protocols to protect user communications. This case study explores Signal's encryption practices and their impact on secure messaging. Key practices. End-to-end encryption. E2EE. Default encryption. Signal uses E2EE by default for all messages, calls, and media transfers, ensuring that only the intended recipients can access the content. Signal protocol. The app employs the Signal protocol, which combines the double ratchet algorithm, pre-keys, and triple Diffie-Hellman 3DH handshake to provide robust security guarantees. Encryption algorithms. Curve 25/5 and AES 256. Signal uses Curve 25/5 for key exchange, AES 256 for message encryption, and HMATCHA 256 for message authentication, ensuring strong security for all communications. ED 25519. The ED 25519 algorithm is used for digital signatures, providing secure and efficient message integrity verification. Key management. Pre-key bundles. Signal servers store pre-key bundles for each user, allowing new sessions to be initiated without requiring both parties to be online simultaneously. Session keys. Each conversation has its own unique session keys, which are regularly updated to enhance security and prevent key reuse. Message encryption and decryption. Encryption process. Messages are encrypted on the sender's device using the recipient's public key and session keys. The encrypted message is then transmitted through Signal's servers. Decryption process. Upon receiving the encrypted message, the recipient's device uses its private key to decrypt the session keys and the message content. Additional security features. Sealed sender. Signal's sealed sender feature hides the sender's identity from Signal's servers, providing an additional layer of privacy. Disappearing messages. Users can set messages to disappear after a specified time, ensuring that sensitive information is not stored indefinitely. Key takeaways. Privacy-first approach. Signal's focus on privacy and security has made it a leading choice for users seeking secure messaging solutions. Advanced cryptography. The use of state-of-the-art cryptographic algorithms and protocols ensures that Signal remains at the forefront of secure messaging technology. Open source. Signal's open-source nature allows for transparency and community scrutiny, enhancing trust in its security practices. Comparative analysis. Similarities. E2EE implementation. All three messaging platforms, WhatsApp, iMessage, Signal, use end-to-end encryption to ensure that only the intended recipients can read the messages. Strong cryptography. Each platform employs robust cryptographic algorithms and protocols to protect communications. User trust. The focus on privacy and security has helped build user trust and drive the adoption of these platforms. Differences. Encryption protocols. While WhatsApp and Signal use the Signal protocol, iMessage uses a proprietary encryption protocol developed by Apple. Platform integration. iMessage is tightly integrated with Apple's ecosystem, while WhatsApp and Signal are available across multiple platforms. Additional features. Signal offers unique features like sealed sender and disappearing messages, which provide additional privacy benefits. Conclusion. The real-world applications of encryption in software, as demonstrated by WhatsApp, iMessage, and Signal, highlight the critical importance of robust encryption practices in protecting user communications. By employing advanced cryptographic techniques, these platforms ensure the security and privacy of their users, fostering trust and widespread adoption. Understanding these encryption practices provides valuable insights into the implementation of secure messaging solutions and the ongoing efforts to safeguard digital communications in an increasingly connected world. Licensing. Understanding software licensing. Types of licenses. Proprietary licenses restrict usage and redistribution. Open source licenses allow usage, modification, and redistribution under specific terms, e.g. MIT, GPL. Legal and practical implications. The choice of license affects how software can be used and shared. Creating licensing agreements. Key components and considerations. Define scope, usage rights, restrictions, and duration. Include clauses for termination and dispute resolution. Enforcing license terms. Monitor compliance and take action against violations. Open source licenses. Compliance and best practices. Ensure adherence to open source licenses when using third-party code and clarify how open source components are used in proprietary software. Impact on proprietary software. Understand the implications of incorporating open source code in proprietary projects. Case studies. Licensing disputes and resolutions. GPL enforcement. BusyBox cases. Overview. The BusyBox cases are among the most prominent examples of GPL, General Public License, enforcement. BusyBox is a software suite that provides several Unix utilities in a single executable file, and it is licensed under the GPL. These cases highlight the challenges and processes involved in enforcing open source licenses. Background. BusyBox in the GPL. BusyBox is widely used in embedded systems, such as routers and smart devices. The GPL requires that any modified versions of GPL licensed software, or software that incorporates GPL licensed components, must also be distributed under the GPL, which includes providing the source code. Enforcement actions. The BusyBox developers, with the assistance of the Software Freedom Conservancy, SFC, and the Software Freedom Law Center, SFLC, have taken legal action against several companies that failed to comply with the GPL by not providing the source code for their modified versions of BusyBox. Key cases. BusyBox v. Monsoon Multimedia, 2007. Claims. Monsoon Multimedia was distributing devices that included BusyBox but did not provide the corresponding source code, violating the GPL. Legal action. The BusyBox developers, represented by the SFLC, filed a lawsuit against Mon Multimedia in the United States District Court for the Southern District of New York. Resolution. The case was settled quickly. Monsoon agreed to cease distribution of BusyBox until they complied with the GPL by providing the source code, and they paid an undisclosed sum to the BusyBox developers. BusyBox v. Verizon, 2008, claims. Verizon was distributing ActionTech routers with firmware that included BusyBox but did not provide the source code, violating the GPL. Legal action. The BusyBox developers, represented by the SFLC, filed a lawsuit against Verizon in the United States District Court for the Southern District of New York. Resolution. The case was settled with Verizon agreeing to comply with the GPL by providing the source code, making a financial contribution to the BusyBox developers, and undertaking measures to ensure future compliance. BusyBox v. Westinghouse Digital Electronics, 2009, claims Westinghouse was distributing digital televisions that included BusyBox but did not provide the source code, violating the GPL. Legal action. The BusyBox developers, represented by the SFLC, filed a lawsuit against Westinghouse in the United States District Court for the Southern District of New York. Resolution. The case was settled with Westinghouse agreeing to comply with the GPL by providing the source code, making a financial contribution to the BusyBox developers, and implementing compliance measures for future products. Key takeaways. Importance of compliance. These cases underscore the importance of complying with open-source licenses. Companies must understand and adhere to the requirements of licenses like the GPL when using open-source software. Enforcement mechanisms. The successful enforcement actions taken by the BusyBox developers demonstrate the effectiveness of legal mechanisms available to uphold open-source licenses. Education and awareness. These cases highlight the need for better education and awareness about open-source licensing obligations among developers and companies. Oracle v. Google. The Java API dispute. Overview. The Oracle v. Google case is a landmark legal battle over the use of Java APIs in Google's Android operating system. The case has significant implications for software licensing and intellectual property rights in the tech industry. Background. Java and Android. Google used Java APIs to develop Android, a mobile operating system. These APIs were originally developed by Sun Microsystems, which Oracle acquired in 2010. Claims. Oracle claimed that Google's use of Java APIs in Android violated Oracle's copyrights and patents, as the APIs were licensed under specific terms that Google allegedly did not adhere to. Legal issues. Copyright infringement. Oracle argued that the structure, sequence, and organization of the Java APIs were protected by copyright, and that Google's use of these APIs without a license constituted infringement. Fair use defense. Google contended that its use of the Java APIs was a fair use, a legal doctrine that allows limited use of copyrighted material without permission under certain circumstances. Court proceedings. District Court 2012. The jury found that Google had indeed copied the Java API packages, but it was undecided on whether this constituted fair use. The district court ruled in favor of Google, stating that the Java APIs were not copyrightable. Federal Circuit 2014. On appeal, the Federal Circuit reversed the district court's ruling, holding that the Java APIs were copyrightable, and remanded the case to determine whether Google's use constituted fair use. District Court 2016. A second jury trial found that Google's use of the Java APIs was fair use. Federal Circuit 2018. Oracle appealed again, and the Federal Circuit reversed the jury's fair use finding, ruling in favor of Oracle and remanding the case for a determination of damages. Supreme Court 2021. The U.S. Supreme Court ultimately ruled in favor of Google, holding that its use of the Java API packages in Android was a fair use. The court recognized the transformative nature of Google's use and emphasized the importance of fair use in the context of software development. Key takeaways. Transformative use. The Supreme Court's decision highlighted the importance of transformative use in determining fair use, particularly in the context of software and APIs. API copyrightability. The case left some questions about the copyrightability of APIs unresolved, as the Supreme Court focused more on the fair use defense. Impact on developers. The ruling provides some reassurance to developers about the ability to use APIs to foster innovation, but it also underscores the need for careful consideration of licensing terms and fair use principles. Jacobson v. Katzer. Artistic license enforcement. Overview. Jacobson v. Katzer is a key case in the enforcement of open-source licenses, specifically the artistic license. The case addressed whether violations of open-source licenses could be enforced through copyright law. Background. Open-source software. Robert Jacobson developed and distributed software for model train enthusiasts under the artistic license, an open-source license. Allegations. Jacobson alleged that Matthew Katzer and his company, Came Ind Associates, Inc., used his software in violation of the artistic license terms, which required attribution and adherence to other conditions. Legal issues. License enforcement. The central issue was whether the terms of the artistic license were enforceable under copyright law, given that the license allowed free use of the software under certain conditions. Court proceedings. District Court. The District Court initially dismissed Jacobson's copyright claims, stating that the artistic license was a non-exclusive license that did not require compliance with its conditions. Federal Circuit 2008. The Federal Circuit reversed the District Court's decision, ruling that the conditions of the artistic license were enforceable under copyright law. The court emphasized that the license granted rights to use the software only if the conditions were met. Key takeaways. Enforceability of open-source licenses. The case established that open-source licenses, like the artistic license, are enforceable under copyright law. This ruling reinforced the legal strength of open-source licenses. Conditional licensing. The decision clarified that licenses can impose conditions on the use of software, and that failure to comply with these conditions can constitute copyright infringement. Impact on open-source communities. The ruling provided greater confidence to developers and contributors in the enforceability of open-source licenses, encouraging continued participation in open-source projects. VMware v. Christoph Hellwig, GPL enforcement in Europe. Overview. This case involved Christoph Hellwig, a Linux kernel developer, and VMware, a company that provides virtualization software. The dispute centered around VMware's alleged violation of the GPL in its use of Linux kernel code. Background. GPL and the Linux kernel. The Linux kernel is licensed under the GPL, which requires that any derivative works also be licensed under the GPL and that source code be made available. Allegations. Hellwig, supported by the Software Freedom Conservancy, SFC, claimed that VMware's ESXi product incorporated GPL-licensed code without complying with the GPL's requirements to provide the corresponding source code. Legal issues. Derivative works. A key issue was whether VMware's ESXi product was a derivative work of the Linux kernel, thus requiring compliance with the GPL. GPL compliance. The case also addressed whether VMware had met its obligations under the GPL to provide source code for the GPL-licensed components. Court proceedings. German District Court. The case was filed in the Hamburg District Court in Germany, which ruled in favor of VMware, stating that Hellwig had not sufficiently demonstrated his authorship of the specific code in question. Appeals. The SFC and Hellwig considered further legal action, but the case highlighted the challenges of GPL enforcement, particularly improving authorship and the derivative nature of software. Key takeaways. Challenges of GPL enforcement. The case underscores the difficulties in enforcing the GPL, especially in complex software projects, where proving authorship and compliance can be challenging. International enforcement. The case highlights the complexities of enforcing open-source licenses across different legal jurisdictions, with varying interpretations of copyright and licensing laws. Developer rights. The dispute emphasizes the importance of clear documentation and attribution in open-source projects to support potential enforcement actions. Conclusion. These case studies illustrate the complexities and challenges involved in enforcing open-source licenses. Key lessons include legal strength of open-source licenses. Successful enforcement actions demonstrate that open-source licenses are legally enforceable, providing a solid foundation for protecting developers' rights. Importance of compliance. Companies must understand and comply with open-source licensing requirements to avoid legal disputes and potential penalties. Educational value. These cases highlight the need for better education and awareness about open-source licensing obligations among developers and organizations. Impact on innovation. Ensuring compliance with open-source licenses helps maintain the integrity of the open-source ecosystem, fostering continued innovation and collaboration. By understanding these landmark cases, developers and organizations can better navigate the complexities of open-source licensing, ensuring compliance and fostering a healthy, collaborative software development environment.